In this part, we use trigonometric identities to integrate certain combinations of trigonometric functions. In the first part, we have sine and cosine function in the integrand. We have three cases for this kind of functions. Case 1, if the power of cosine is odd, that is if n is 2k plus 1, we save one cosine factor and use the identity cosine square x is equal to 1 minus sine square x to express the remaining factors in terms of sine x. In this case, the given integral becomes c, the power of cosine is 2k plus 1. So we write sine function first, sine to the power mx times we save one cosine factor. So we have cosine to the power 2k, not 2k plus 1. And I write cosine x dx here. So I save one cosine function. And instead of cosine x, we write 1 minus sine square x. In this case, the function becomes, instead of cosine, we have 1 minus sine x, sine square x to the power k, and the rest of the function. In the final step, we use u-Substitution. We say u is equal to sine x. Let's understand the first case by an example. We only have cosine function in the integrand. This integral is equal to, we first save one cosine function, so cosine cube becomes cosine square x times cosine x dx. This is equal to, instead of cosine square x, we have 1 minus sine square. 1 minus sine square x times cosine x dx. And we use substitution. We say that u is equal to sine x. In this case, du becomes cosine x dx. Let's use this substitution to solve the integral. In this case, we have integral 1 minus u square. Instead of cosine x dx, we have du. It's very easy to integrate this function. The answer is u minus u cube over 3 plus c. And finally, instead of u, we should write sine x. This is the final answer of this integral. In the second case, the power of sine function is odd. That is m is equal to 2k plus 1. So in this case, we save one sine factor and use the identity sine square x is equal to 1 minus cosine square x. We use this identity to express the remaining factors in terms of cosine. Finally, this integral becomes, instead of, we first save sine factor. So we have sine to the power 2k instead of 2k plus 1 x times cosine to the power n x. We have one more sine, so we have sine x dx. Instead of sine square, we should write 1 minus cosine square. 1 minus cosine square x to the power k times cosine to the power nx sine x dx. And we use the u-Substitution. We say u is equal to cosine x and do the rest. Let's try to understand this case with an example. This is equal to, the power of sine is odd as you see. So we save one sine factor. Sine, instead of sine to the power 5, I write sine to the power 4. And instead of sine to the power 4, I write sine square times, we have cosine square. And since I save one sine factor, I write here sine x dx. This is equal to integral, instead of sine square, we have 1 minus cosine square x square times cosine square x sine x dx. Now we are ready to use substitution rule. We say that u is equal to cosine x, du becomes minus sine x dx. Let's use this substitution. In this case, the integral becomes, instead of 1 minus cosine square, we have 1 minus u square. Instead of cosine square, we have u square. Instead of sine x dx, we have minus du. Let me put minus in front of the integral, and we have du. This is equal to, we have minus here, integral of u square minus 2u to the power 4 plus u to the power 6 du. It's very easy to find antiderivatives for these functions of u. Let me write the final answer in terms of x. I use back substitution. Finally, I have 1 over 3 cosine cube x, since u was cosine function, plus 2 over 5 cosine to the power 5x minus 1 over 7 cosine to the power 7x. And finally, since the integral is indefinite, we have to add a constant c. Look at the powers of sine and cosine. They are both even functions, even numbers. They are both even numbers. So in this case, I should write the integral as 1 minus cosine 2x over 2. This is trigonometric identity for sine function. And for cosine function, we have plus version, 1 plus cosine 2x over 2. Since the power of cosine is 4, we have cosine square square. This is why we have square here, dx. This is equal to, you have 2 in denominator and 4 in denominator. This is why I take the parentheses of 1 over 8 and continue to write the integral. We have 1 minus cosine 2x times 1 plus cosine 2x square. This becomes 1 plus 2 cosine 2x. Using the binomial expansion, we have cosine square 2x, okay, dx. This is equal to, if you substitute all this integrand, then you have 1 over 8 integral 1 plus cosine 2x minus cosine square 2x minus cosine cube 2x dx. And if you integrate this function, you get 1 over 8, 1 over 16, the parentheses of 1 over 16, x minus 1 over 4 sine 4x plus 1 over 3 sine cube 2x and a constant c. I don't want to go to details of the last step. Please be careful how to integrate cosine square 2x and cosine cube 2x. Now we have a new type of trigonometric integral. In this type, we have tangent and secant functions in the integrand. We have two cases. In the first case, the power of secant is even, that is n is 2k. In this case, we save a factor of secant square x. We save a factor of secant square x and use the trigonometric identity. Secant square x is equal to, as you know, 1 plus tangent square x. we use this trigonometric identity to express the remaining factors in terms of tangent x. In this case, the integral becomes tangent to the power m x. Instead of secant to the power 2k, I have secant square x to the power k minus 1, and I save 1 sine square x function dx. And in this step, I use this trigonometric identity. The integral becomes tangent to the power m. We don't change this part. Instead of secant square, I have 1 plus tangent square x to the power k minus 1. And if you use u-Substitution, if you say u is equal to tangent x, and du in this case becomes derivative of tangent is secant square x dx, so this part becomes du. But now I don't apply u-Substitution. I only write the rest of the question as secant square x dx. Let's look at the problems. As you see, in the first case, the power of secant is even. And in this problem, the power of secant is even. This is 4. I should save 1 secant square function. We have tangent to the power 6 x times secant square x, and save 1 secant square x. Instead of sine square x, I have 1 plus tangent square x. And finally, the rest is secant square x dx. In this step, I want to use substitution rule. Let's say u is equal to tangent x, and differentiating each side, I have du is equal to secant square x dx. Let's use this substitution in this step. The integral becomes, instead of tangent to the power 6, I have u to the power 6. Instead of 1 plus tangent square x, I have 1 plus u square. Instead of secant square x dx, I have the u. Let's rewrite the final step. I have u to the power 6 plus u to the power 8 du. It's very easy to integrate this function. I have u to the power 7 divided by 7 plus u to the power 9 divided by 9 plus c. I should use back substitution since u is tangent x. Instead of u, I should write tangent. So this is tangent to the power 7 and tangent to the power 9. This is all. In the second case, if the power of tangent function is odd, we save one secant x. Let me write down here, secant x, tangent x factor. We save this factor and use the trigonometric identity. Tangent square x is equal to 1 minus, no, not minus, secant square x minus 1. If the power of tangent function is odd, in this case, we save a factor of secant x, tangent x. We save this factor and use the trigonometric identity. Tangent square x is equal to secant square x minus 1. We use this to express the remaining factors in terms of secant x. In this case, this integral becomes, instead of tangent to the power 2k plus 1, I save 1 tangent from here. So I have tangent square to the power k. I save 1 secant, as you see. I save 1 secant and 1 tangent. So instead of secant to the power n, I say I have secant to the power n minus 1 x. So I have secant x tangent x. Secant x tangent x dx. In this step, if you use this trigonometric identity, the integral becomes, instead of tangent x, tangent square, I have secant square x minus 1 to the power k, secant to the power n minus 1x times secant x tangent x dx. Okay, and finally we use u-substitution. We say u is equal to secant x, and we continue to apply u-substitution. Let's try to understand this case with an example. Since the power of tangent is odd, I can use this case. I first save one tangent and one secant factor. Instead of tangent to the power 5, I write tangent to the power 4. Instead of secant to the power 7, I write secant to the power 6. Since I save one tangent and one secant, I write them here. In this step, I use the trigonometric identity. Since tangent square is secant square minus 1, I have secant square x minus 1 square instead of tangent to the power 4. I have secant to the power 6. Okay, I don't change this part. And I have also tangent x, secant x or tangent x, okay, dx. In this case, I use u-substitution. I say u is equal to secant x du, differentiating each side of this equality, secant x tangent x, secant x tangent x dx. I use this substitution in this step. In this case, the problem becomes, instead of secant x, I have u minus 1 square times u to the power 6. Instead of this, I have du. Finally, if you substitute this expression, you can easily find the antiderivative of this function. Let me write down here. 1 over 11, and I also use the back substitution, secant to the power 11x minus 2 over 9 secant to the power 9x plus 1 over 7 secant to the power 7x plus c. This is all. This is the final example of this part. Since the power of tangent is odd, I should say one tangent factor. Instead of tangent cube, I have tangent times tangent square, tangent x times tangent square x dx. Instead of tangent square x, I use secant square x minus 1, so tangent x times, instead of this, I have secant square x minus 1 dx. This is equal to, if you substitute this expression, you have integral of tangent x secant square x from here minus integral of tangent x dx from here. And for this part, if you use substitution rule, let's say u is equal to tangent x. In this case, du becomes secant square x dx. If you use this substitution for the first integral becomes tangent square x over 2, and the second integral is minus ln secant x, we have to add a constant c. This is all.